Hey students, Professor Nugent here. Let's finish up chapter 5. We're going to talk about when the student t distribution applies. We will use the student's t distribution for inference if our OLS residual u is both homoscedastic and normally distributed. Recall that we have these 5 assumptions. We have added 2 assumptions to our list of assumptions that we are making about our least squares analysis to help us develop an estimator. We have added that we are assuming that u is homoscedastic and that u is normally distributed with a mean of 0 variance sigma square. Okay, so if all 5 assumptions hold, that we see that beta naught and beta 1 hats, they are normally distributed for all n, and the test statistic has a student t distribution with n minus 2 degrees of freedom, and this holds exactly for all n. Right? We mean for all n, I equals 1 through n. So in the case that we have 4 holding, 5 holding, in addition to 1 through 3, then the test statistic has a student's t distribution for all n, for all sample sizes, whether our sample size is small or sample size is large. Let's look at the normality of the sampling distribution under assumptions 1 through 5. We have defined the difference between beta 1 and beta 1 as this expression. This should be familiar by now, and we can rewrite this expression as 1 over n times the sum from I equals 1 to n of wi times ui, where wi is the ratio of xi minus x bar over 1 over n times the sum from xi of xi minus x bar squared. Okay, this is how we're defining wi. And wi is the OLS weight. Okay, is the OLS weight on the residual. So let's ask, what is the distribution of the weighted average of normally distributed random variables? That's what I think what we mean by here by normally distributed random variables, normal random variables. Under assumptions 1 through 5, we substitute wi into our understanding of the distribution of beta 1 hat minus beta 1, and that gives us the homoscedasticity only variance formula. Okay, so this is that. So beta 1 hat minus beta 1 is normally distributed with a mean of 0 and a variance of 1 over n squared times the sum from I equals 1 to n of wi squared times the variance of the OLS residual. The variance of the OLS residual. Okay? So this is the distribution of the weighted average of the normal random variable. Our null hypothesis and test statistic, as we have said, will have a student's t distribution with n minus 2 degrees of freedom. Now why n minus 2? That's because we have estimated 2 parameters, beta naught and beta 1. So we knock off these 2 degrees of freedom, and that allows for a little bit more uncertainty in the error. Okay. Now for small sample sizes, less than 30, our students' t-distribution critical values, they're going to be a bit larger than what we would find using the standard normal distribution. And so that is really where this makes a difference, where you have a small sample. If you can satisfy assumptions 1 through 5, this becomes useful. For large samples, like n greater than 50, the difference between the student's t-distribution and the standard normal distribution, it's negligible. Okay, so if you recall the student's t-table, it's organized by degrees of freedom. We can look at the 5% t-distribution critical value. For 10 degrees of freedom, the critical value is 2.23, and the critical value decreases as the degrees of freedom go up. For 60 degrees of freedom, the critical value is 2, and as you move to infinite degrees of freedom, you move to our familiar 1.96. Observe that 1.96 is very close to 2. So for large samples, the student's t-distribution quite close to the normal distribution. If we think practically, if our sample size is small and you have evidence that, or you believe that for your application, the OLS residual is homoscedastic and normally distributed, then use the student's t-distribution instead of the standard normal critical values for hypothesis tests and confidence intervals. But in most econometric applications, there's no reason to believe that the OLS residual U is homoscedastic and normal. Usually there are good reasons to believe that neither assumption holds, that we have heteroscedasticity and non-normal distributions, especially if you're working with financial data or other things like this, where you have skewed distributions. Unfortunately, in modern applications, typically our data sets are bigger than 50. We're working with data sets in the thousands, tens of thousands, hundreds of thousands. I've personally worked on data sets in the millions. And so in that case, we can rely on the large N, the law of large number, the large N results. And based on the central limit theorem, the large N results, we can use the central limit theorem, which gives us that as our sample size grows larger, that it's going to approximate a normal distribution, and so we can perform hypothesis tests, construct confidence intervals using the large N normal approximation derived from the central limit theorem. Now let's conclude this chapter. We had an initial policy question. If we supposed that new teachers are hired, so the student-to-teacher ratio falls by 1 student per class, we may ask, what is the effect of this policy intervention on test scores, right? We had a district superintendent who wanted to prove that decreasing the student-to-teacher ratio, the intervention or treatment, would lead to an increase in test scores. This question requires an estimate of the causal effect on test scores of a change in the student-to-teacher ratio. Does our regression analysis using the California dataset provide a compelling estimate of this causal effect? And the answer is not really. We have been discussing all along that students with a low student-to-teacher ratio tend to be districts with lots of resources and higher income families, which provide kids more learning opportunities outside school, and so the kids are likely to have higher test scores due to these confounding factors. Alright, confounding factors are factors that affect both the independent variable and the dependent variable. This suggests that the correlation between the OLS residual and the student-to-teacher ratio is positive, right? Because we have confounding factors. Factors in the OLS residual that are related to the student-to-teacher ratio. So they are correlated. The correlation is positive. So we have failed. The assumption number 1 is not valid. But we can work on this. All hope is not lost. We can work on bringing these factors into our regression analysis, okay? Because we have omitted them. We have omitted some factors, some variables, like income. And if we bring that into our regression, we can work on satisfying least squares assumption 1, which is going to help us drive to providing a compelling estimate of a causal effect. Okay? Thanks, students. That's it for chapter 5.